Now let's talk about dissolving metal reduction. Now in this video we're going to focus on hydrogenations, but there are other dissolving metal reduction reactions. Now this works using a radical mechanism, but in a lot of the other videos in this series, the radicals generated a chain, and then those chains propagated, right? So we initiated a radical formation, propagated the chain, and then at some point there was enough terminations that the reaction stopped. In dissolving metal reductions, there's no chain of events. It just kind of happens. And so we have a metal, which is sodium, and here is its valence electron. And if we dissolve this in ammonia, which will have to be kept at a low temperature just to keep the ammonia liquid, then we can produce solvated electrons. Now, these electrons are not really attached to any particular atom. They are in the solution and available for reaction, and they're relatively reactive. And as such, we can use these to perform hydrogenation reactions. Now, we've already talked about hydrogenation reactions, and specifically, let's look at alkynes. And if we performed a hydrogenation reaction on this using, say, a Lindlar's catalyst or some other poisoned catalyst, we would get syn hydrogenation. That is, the hydrogens would add to the same side of this alkyne. And that has to do with the mechanism. It's interacting with a solid catalyst. And so both of these sides, the same side, will lay down and interact with the metal. And so hydrogenation happens on one side. In this case, everything is dissolved in the solution. So we don't have the restriction of syn addition. So if we have some sodium and ammonia, then we'll have to have it liquid. And so in order to have it liquid, we'll use dry ice temperatures. And then something interesting will happen here. You'll notice that we get the E isomer. So this is an anti-hydrogenation. And it doesn't mean it's against hydrogenation. It just means that it's adding on opposite sides of the molecule rather than syn hydrogenation, which would be adding to the same side. And the real reason this happens is steric hindrance. So once we look at the mechanism of this process, I'll be able to point out a step where steric hindrance would prevent it from going in the cis configuration. So we only get trans configuration, or the E configuration, if you prefer that nomenclature. So here's our solvated electron. and that's going to interact with this carbon here. And again, we're using one arrow there. And that's going to trigger one of these bonds, and I suppose I could draw them both on the same side to indicate it really are coming from the same bond. So I'll just extend that arrow there. And then we'll get a structure that looks like this. Negative charge on the carbon that we've added an electron to, radical on the other carbon. Now, it's at this stage that if we were to try to put this in the cis configuration, that we would have steric hindrance between this group and that group. So that's why it prefers to go into the trans orientation, because this provides the most amount of room available. Now, our ammonia is going to be our source of hydrogen. So these pair of electrons, so since it's a pair, it's a double-headed arrow, we'll do that. And of course, we have our deprotonated ammonia. Now, at this step, the process continues again. We have another solvated electron. And that's going to come in and react with our radical. That places a negative charge on the other carbon that was associated with the triple bond. And then we repeat this same step where we have a deprotonation. And that generates our product. And another deprotonated ammonia. Now, you might look at this and say, well, that's interesting. It did not continue to reduce the double bond here. And that is a feature of this reaction. We're able to stop at the reduction of an alkyne. It will not reduce an alkene. And so just as an example, if we had some reagent here, like so, so we have a cis bond right here, and we're going to be able to make a trans bond there. So we would end up with this product here. And you'll notice that the double bond that existed in the molecule already remains. And then now we've formed a new trans substituted bond here. So now we have options. We can use a poisoned catalyst with hydrogenation to do a heterogeneous hydrogenation, form the cis isomer, or we can use a dissolving metal reduction and form the trans isomer. And this works exclusively on alkynes. So we're able to reduce an alkyne in the molecule while leaving other double bonds like alkenes alone. Now it's possible to do other dissolving metal reductions, and I'll note one down here, and then our next video is going to focus on the Birch reduction, which is another example of a dissolving metal reduction. So step 1, add some sodium, THF, and a little bit of dilute alcohol. We don't want a lot of alcohol because the alcohol will just react with the sodium. So we just want a little bit, and that's just so that we have proton sources during this process. And we're going to need a proton source to supply that the proton for the carbon right there. The proton that is going to go on the oxygen, that's going to be put on by the acid workup step, which is this. So another example of a dissolving metal reduction.